Right, it's 2:02 now. I think we can get started. So hello everyone, welcome to Ask Seminar series. I'm John, the seminar coordinator. I will be moderating today's seminar. Our communication specialist, Kat Medney, is in the middle of another meeting, but she's with us as well. And our associate director, Ralph Ferrero, also joined us, and he will be introducing the speaker before she gets started. Just so you know that this seminar is being recorded, and we will publish the recording on our YouTube channel. And please feel free to check it out. It usually takes about 1 week or so. And after the presentation, we will have the Q&A session, and you can ask a verbal question, or you can chat us your questions, and we will read it aloud. So before the speaker gets started, I will let our Associate Director, Ralph Ferrero, to introduce the speaker. So Ralph, please go ahead.
Yeah, thanks, John. Yeah, I'd like to welcome Dr. Christine Wiedinmyer. I didn't say it quite right. Okay, all right, good. She's at the University of Colorado at the Cooperative Institute there series. Got her PhD in chemical engineering, University of Texas, and her research focus is on pollutants and fires and their transport. Prior to that, she spent some time at I think it was with NCAR NCAR, and also Christine has been the recipient of several awards, professional societies, as well as the state of Colorado. And she's also on several boards as well. And I'm going to turn it over to her, and we'll learn a lot about fires and their impacts to all of us.
Excellent. Thank you so much, Ralph. I really appreciate it. And thanks to John for the invitation. I'm really excited to be here. I'm only sorry that I can't be in person with everyone, but even just looking at the faces, I'm really excited to see everyone. I'm going to try to share my screen. Let's see. And tell me if you can see my slides.
Yep.
Yes.
Super. Okay. Well, today I'm going to talk to you about, my research and lots of work that I've been doing along the way. And again, I'm at the University of Colorado, Boulder at Ceres. But before I get started, I just wanted to wish everyone a happy Mardi Gras. I'm also a Tulane University grad from New Orleans, and so I always like to celebrate Mardi Gras. And for those of you from Pennsylvania, this is also Flash Nut Day, Donut Day. It's another celebration, so I always have donut and king cake. But happy Mardi Gras. I hope you all go out and celebrate today. And again, just a little bit about Ceres. Ceres, we're the Cooperative Institute for Research in Environmental Sciences. We are located at the University of Colorado Boulder, and Ceres has had a partnership with NOAA since 1967. Our institute has over 800 scientific staff, students, postdocs that work either at the university or embedded within 8 different units at NOAA. And for those looking for a job, we're always hiring. Please let me know or check out our job site. And if anyone wants to know more about Ceres, I'm happy to share. Let's see. Also, before I go too far, I want to just acknowledge I don't do anything by myself. I have amazing collaborators and colleagues with whom I work, and here's just a list of some, particularly those who I might present their work today. So I just wanted to give everyone an acknowledgement. And basically, my career has been spent looking at atmospheric pollutants, what goes up into the air and how they impact particularly air quality and climate. And in order to really understand air quality and climate, you have to know what's being put into the atmosphere. And for us to mitigate and any air pollution or climate challenges, we have to know what emissions are going into the air. And so my career I started out looking at biogenic emissions. These are natural organic compounds that are emitted from vegetation, undisturbed vegetation. You think about when you walk through a pine forest and you smell that pine forest smell. Those are biogenic emissions and how they interact in the atmosphere, how they might interact with anthropogenic pollutants. And then I moved towards disturbances of vegetation, particularly wildfires and fires. And that also led me to some studies looking at other biomass burning from residential heating and cooking across the world. And I've been fortunate enough to have support from many different agencies, some of them listed here. So today I'm going to focus on fire, and this is an old figure, but I really like it because it really just shows where fire activity happens across the globe. And one thing to note here is that, you know, pretty much wherever we have vegetation, fires might occur. And some places you get more fire, but really where we have vegetation, fires happen. And this could be wildfires, prescribed burning, agricultural burning, or land clearing. Because these are, this is based on satellite observations, so observations of fire activity from space. So it could be any of these types of fires. And my work has really focused on the emissions of, that are produced from fires. And these emissions can be a lot of different things. We have reactive gases such as carbon monoxide. You'll see me use non-methane organic compounds or non-methane organic gases and OCs, sulfur dioxide, ammonia, nitrogen oxides. You also have greenhouse gases like methane and carbon dioxide that are emitted from biomass burning. You can have toxics such as mercury or dioxins emitted during combustion processes. And then a whole host of inorganic compounds that can be emitted when biomass is burned. And then we have particles, particulate matter. You might hear me say PM, that's particulate matter. And then that particulate matter can be made up of a lot of different things, but you know, in particular, we focus on organic carbon and black carbon that are formed through different combustion processes. The organic carbon you might think of as more white in color, whereas the black carbon is darker. So I spent a lot of my career working on these different modeling efforts to predict emissions of air pollutants to the air from open burning. I started with looking at just North America and expanded that into a global inventory that is called FIN, the Fire Inventory from NCAR. Just an aside, I was in a group that studied emissions from vegetation, and my group lead at the time, Alex Gunther, named his model the model of emissions of gases in nature, aerosols from nature, or Megan, after his daughter. So when it came time to name my model, I named it Finn because my son is named as Finn. So he thinks he's famous. But anyway, we just submitted an updated version, but basically the goal was to have a high resolution, both in time and space, emissions inventory that could be used for a host of applications. I geared this mostly towards air quality applications, but it has been used for a whole bunch of different studies. And basically, the model can predict emissions of anything that's been measured from wildfires. In general, emissions are a function of biomass that's burned, the vegetation that's burned, how that vegetation is burned, and the intensity or the type of fire, as well as the emission factor or the mass of pollutant that's emitted per mass of biomass burned. We take a pretty bottom-up approach. We use satellite maps of vegetation, and then fire detections, detections from space of where fires are burning and when, and then overlay them together to understand and estimate how much fuel is burned when and where. I've been fortunate enough to work with amazing chemists and atmospheric scientists over the years who have taken measurements of air pollutants either in the lab, and this is a picture from the Montana Fire Sciences Laboratory. And in this lab, they take certain biomass fuels and put it on, let's see, I don't know how to do that. Okay, I don't know how to do the arrow. I don't know if you can see my arrow. But they put it onto a bed where they can weigh the fuel. They set it on fire, and then the plume goes up into either fills up the room or it goes up into a chute and from that people can measure different pollutants and samples. There's also been a whole host of aircraft campaigns where scientists load up aircrafts. A commonly used one is the NASA DC-8 or also the NCAR C-130. And then they can fly through fire plumes and come up with predictions of pollutant emissions from real integrated fires. This is just a picture from one study in Brazil. What's exciting to me is there's been amazing studies that happened in 2018 and 2019 that have really provided a wealth of new information about wildfire pollutants. One thing that I love everyone to walk away from, if you know nothing about fires, is that smoke and what's emitted by fires is not one thing. It is a whole host of many different things, from greenhouse gases, like I mentioned, reactive trace gases, hazardous toxic pollutants. And this is just a list of just a few of them. So there's not one thing emitted, right? Some are hazardous pollutants and they have different impacts depending on what they are. And I'll talk a little bit more about that in just a minute. Just a little bit about our latest version of FIN. We've updated our burned area estimation. We've included not only the MODIS fire detections, which was what our original model was based on, and what we also include VIIRS fire detections. We have updated our vegetation data sets that we use, emission factors and fuel loadings, and we've made this open source and flexible so that others can go in and use it. We're also putting it into forecast mode so that it could be used for forecast modeling as well as hindsight modeling. This is just some results from the FIN emission estimates. The different colors are showing you different regions of the world. And you can see, just this is carbon monoxide emissions by month, averaged over 2012 to 2019. And you can just see that, globally, we have two peaks in fire emissions, really driven by the tropics and Africa, South America, and Southeast Asia, and Equatorial Asia. I really like to highlight how important fires are to the overall composition of the atmosphere. Even when you're comparing it to fossil fuel combustion, the amount of carbon that's released into the atmosphere is pretty substantial. And then we look at more reactive gases, such as carbon monoxide, nitrogen oxides, and then these non-methane organic compounds. The biomass burning, which is the red piece of these pies, is pretty significant. So when we're trying to understand air quality and atmospheric composition, these emissions are really important. And they're particularly important when we're looking at particulate matter emissions. I talked about particulate matter, or PM. PM 2.5 are those fine particles that you can breathe in and they cause health problems. It's what we look at from air quality control measures. Organic carbon is OC and black carbon is BC. So when we're looking at biomass burning, these emissions dominate the global emission inventory. And so if we're going to understand health impacts as a result of particle pollution, as well as climate impacts, it's really important that we get these emissions right. And just a side note, if you combine both the residential biomass burning and the open biomass burning, 73% of the global black carbon particle emissions and 93% of the global organic particle emissions, global organic carbon emissions are from burning processes. So again, I just want to highlight how important these sources are. And of course, have many different impacts. The first I just want to mention is air quality. And this is a satellite image from just a couple of years ago in August 2020. We had huge fires burning across the California and the Pacific Northwest. And just to highlight, like, you don't only have these local impacts across Oregon, Washington, and California, but you can see the smoke can transport well across the US. And we see that in our forecast. This is a forecast from the NOAA, her smoke model that from around that same time period. And you can see that you have large particle concentrations. This is vertically integrated smoke. So the smoke in the vertical column, and you can see you have really strong particles off the West Coast, but also they can reach all the way across the continental US. And we see that in our air quality monitors. This is just a snapshot from around that same time period where you see the air quality or the particle concentrations is quite high, particularly where the particles are, but you can see the influence across the country. And there's been a lot of really interesting work looking at the biomass burning contributions to surface PM 2.5. This is a paper I love to highlight because it shows what I'm showing you here now is the fraction of PM 2.5 attributed to wildfires for the summer season. For all days that had PM above 35 micrograms per meter cube. This is the health standard at the side, like that's what EPA regulates, right? So on, this is on all days, maybe biomass burning contributes up to 25% of the PM 2.5 concentrations. Sorry, but if we look at those days that exceed those national ambient air quality standards or health standards, you can see that in the Western United States, wildfires drive those exceedances of the EPA's national ambient air quality standards. They contribute, 90 to 95% of that PM that's driving those exceedances. So this causes a huge, this is extremely important and causes a huge challenge for those trying to manage air quality across the West. And here's another great paper that just came out recently by David et al. From Colorado State University. And really, it just takes different regions across the US and shows how much the number of exceedance days for ozone, PM 2.5, and PM10. PM10 is the coarser particles, and how much different sources, wildland fires, agricultural fires, stratospheric intrusions, et cetera, contributed to those exceedances. And the point here is that if you look at regions 8, 9, and 10, the red bar is pretty substantial, which means that wildfires are contributing not only to exceedances of PM 2.5, but also of ozone, which is also the case in the Southeast United States, where we have not only some wildfires, but we have a lot of prescribed burning as well. I just want to mention that, not only do biomass burning emissions impact weather, air quality, but they also have impacts on weather and climate. And just as a cartoon, we have aerosols being directly emitted into the air and contributing to particle concentrations in the atmosphere. We also have these trace gases, some of which can react and form secondary organic aerosol and then contribute to the aerosol formation in the atmosphere. That aerosol can both diffuse and absorb radiation through the atmosphere. They can also act as ice nuclei and cloud condensation nuclei, so impacting clouds and cloud formation and having indirect effects on radiation. And then even potentially feedback on precipitation. We did a study a while back using the WRF-Chem integrated meteorological and chemistry model to look at these feedbacks between some wildfire smoke and particles and weather. And what we found is we looked at these fires that happened in I want to say 2007 right now, in Idaho and Montana, and simulated them within the model. And we found that we saw changes in boundary layer depth, in surface temperature, and in surface solar radiation by including these emissions. And they did have feedback on the simulated chemistry, so much so that we saw really large changes in our predicted ozone concentrations when these feedbacks were included. And once these emissions are into the atmosphere, they do impact health. And I'm just going to point to work by Colleen Reed and others. They put together a really nice summary or review a few years back, and there's been a lot of updates since. But exposure to wildfire smoke has led to premature death and other morbidities. They've been associated with respiratory infections and other types of outcomes, including birth outcomes. I'm not going to go into details here, but there's some really awesome people working on looking at the health effects from wildfires, and I'm happy to share their research papers with you if you're interested. We know a lot about wildfire smoke, but there's still huge uncertainties in all components of this research that I just spoke of, from the emissions to understanding the transport and chemistry to looking at the impacts. And this is just a picture I took actually a month after the earlier pictures. This is just on a hill when I was driving to work or driving home from work, looking over Boulder when we had 3 or 4 different fires, both locally and regionally going on. The first is, a lot of the fire emissions models rely on satellite detections of when and where a fire is burning. And of course, these in themselves have challenges. This is just showing you the difference between including MODIS and then MODIS and GOES fire detections. This has to do with the orbiting, the orbit that the satellites are on, the timing, the sensitivity, etc. And you can imagine that if you used one group of fire detections versus another, you might get really different results in your predictions of emissions if your model is being driven by these detections. One of the things I think is the biggest driver right now, or one of the largest drivers of uncertainties in our emission estimates, is land cover and understanding the fuel that is actually being burned. We have a pretty simplified fuel mapping and model within FIN. And what we do is we take satellite-derived vegetation maps and simplify them into generic vegetation codes to which we assign fuel loadings. But you could see here, this is 2 different global land cover data sets that have been simplified down into the FIN generic codes. And you can see that the top one is mostly grasslands, which is the lighter green, and orange shrublands and shrublands and woody savannas, whereas the bottom one gets mapped to woody savannas and shrublands, and then the darker green is forests. So you can imagine if you're predicting a fire at a certain point, if you're burning shrubland or grassland, you might have a very different fuel load, a very different fuel burned than you would if you had a evergreen or a temperate forest. So again, getting the fuel loading is really important and can lead to big discrepancies between fire emission predictions. We've been comparing our estimates with other emissions estimates. This is just showing you monthly CO emissions for the Northern Hemisphere Africa and the Southern Hemisphere Africa. And the point here is that we even get different seasonality depending on which model you're running. And you can have a factor of 3 to 4 difference in emission predictions. So I think there's some work to be done to really validate and better understand where we're getting things right, where we're not, how we can take advantage of advances in one model and bring them to another, et cetera. I think there's a lot of value in having these different models for comparison and really teasing out the important drivers of fire emissions. And again, these emission differences have huge impacts on our predicted impacts. And this is a great paper by Tess Carter a few years ago, where she looked at different inventories in boreal North America, contiguous US and globally. You can see down here on the bottom, this is particulate organic carbon and the annual emissions between the different inventories, and they're quite different, as much as a factor of 4, depending on where and what you're looking at. But the big point here is that when you put them into global climate models, you can get very different results, very different radiative impacts. And so again, this highlights the need to better constrain our emission inventories, because we need to get our climate predictions and understanding impacts correct. So the other big work that I've been looking at is looking at the chemistry and how we simulate the chemistry of wildfire emissions. When we first did FIN originally, we based it on this paper by Cheryl Akaki in 2011, where she provided 93 emission factors for non-methane organic gases. And at that time, about 50% of the organic gases that were measured in plumes were actually identified. That has advanced tremendously in the last 10 years. The chemists out there are amazing. Their tools are amazing. It's just been great. But now, there have been studies where over 700 non-methane organic gases have been identified. And for example, from the recent WECAN campaign in 2018 in the Western US, Permar et al. Published 161 emission factors. The challenge now is, how do we take these hundreds of compounds and simplify them down into something that a chemical air quality model can use? Because of the complexity of air quality chemistry or atmospheric chemistry, a lot of air quality models have to simplify the chemistry, come up with lumped species to simulate different groups of chemical reactions. And one of the great things that I'm so excited about recently is Kelly Barsanti and her student have been leading the development of NEVA, which is a new emission inventory database that brings in all published emission factor emission data available and puts it into one consistent format. The other brilliant thing that they do is they have consistent terminology across all compounds, and they've actually mapped all species and provided recommendations to how to simplify all these different compounds into specific chemical mechanisms used in air quality models. So we can have consistent modeling of these organic gases. And this is important because the assumptions we make, like say we have 1,3,5-trimethylbenzene, and if we assume it gets lumped into X versus Y, you could have very different results, just even in the distribution of the chemicals in your air quality model. And this could have big impacts on the way that we model the chemistry downwind. And this is just an example from box model simulations where we're simulating ozone over time and using 2 different assumption data sets for these VOCs. And you could even get, 10 ppb difference in your predicted ozone just by making different assumptions on your organic compounds. But you can have big impacts on, say, downwind formaldehyde production, PAN and the nitrogen species, as well as terpene oxidation products, or these are all organic aerosol precursors, secondary organic aerosol precursors. So again, the point here is the assumptions that we make on how to assign various chemicals into our chemical mechanisms used for air quality models is extremely important. One of the things that, one of the directions I went, how about that? When I was doing this biomass burning research was, it led me to looking at the other fire sources. This includes biomass burning from cooking and heating, as well as open waste burning. I was fortunate enough to lead an amazing project in northern Ghana between 2011 and 2016, looking at air quality, climate, and cooking technologies in northern Ghana. This was a highly interdisciplinary project. I just provide some overview here, but looking at the emissions, from cooking, measuring the emission factors, looking at behaviors and willingness to pay for new technologies, and how these impact the area. And if anyone's interested, I'm happy to follow up and talk more about that project. When I was in northern Ghana, one of the things that I noticed was that there was no waste management and everyone burned their trash. And I went looking at that time and found that a lot of the emission inventories used for global modeling applications do not include the emissions, open emissions of burning waste. And when I wanted to ask, is this an important source and something that we need to look at further? And with colleagues from Montana and EPA, we came up with a waste burning emissions inventory that I think has really motivated more measurements across the globe now looking at waste burning. And there's lots of opportunity to improve this. But it was an important source, particularly in certain countries and certain regions of the world. This also led me to work with Eloise Murray, who's at the University College of London currently, to come up with an emission inventory for Africa. It's a place that's rapidly changing, lots of emissions that I didn't think about when I lived in the US or as a person living in the US. So we came up with an emission inventory, including all these inefficient combustion sources. That is now anyone modeling Africa and global chemistry can use these emission inventories in their models. I think there's a lot of opportunity to improve. And Eloise has gone on and really done a nice job constraining the emissions associated with charcoal production, as well as power ships and other sources unique to the region. I have, I have a lot of other research activities. I've kind of just given you a highlight here, but looking at fires in northern latitudes and their impacts on the Arctic, looking at fires into the future and their impacts as climate changes, as weather changes, and then looking at emission inventories, for example, from other sources. I live in the state of Colorado. Cannabis for recreational use was legalized a few years back, and it led to a lot of questions about their environmental impacts. And so it led to some papers with Will Visuete and Chitsan Wang to look at those emissions and potential impacts. I also want to highlight two recent National Academies workshops on wildland fires, and then the chemistry of urban wildfires. And I really recommend if you're interested to go back and look at these two workshops. Are available to view online, as well as all the talks. When I was first asked to give a talk at the one on urban wildfires, I didn't take it very seriously. I didn't think that urban wildfires were a significant source of emissions, particularly when we're looking at the Western United States. And that workshop really let me think of things differently. And I want to spend my last bit of this talk talking about urban wildfires. And this is just a map showing you where structures have been lost to wildfire across the United States since between 1999 and 2016. And there's been some really large fires that have burned significant number of structures. And some of those are just listed on the right there. And the question there is, what are the emissions when these structures are burned, when you have a fire go through an urban area? What are the emission factors? And then how do we figure out how much is released? And I think there's a lot that need to be learned. And this is just, similar to biomass burning or wildland fires. You have materials burned and the activity associated with that, and then what is emitted. There has been some work to look at the emissions that are associated with burning of structures in urban areas. And this is just showing you emission factors for different articles that you might find in an urban area compared to what you would see from Western wildfire. These emission factors have been, I really have to acknowledge Amara Holder from the US EPA. She's really led this research and really led the compilation of understanding what we know from urban wildfires and their impacts. But you can see that, you know, some of these emission factors are, you know, 5, 6, 7 times larger than what you would get from a wildfire. So even if you burn less, you might have more emissions. And Amara put together an emissions inventory from the Paradise Fire from November 28th, or the Camp Fire that went through the town of Paradise in California and burned over 18,000 structures and I don't know how many cars. And you can see here, like this is a log scale, but the wildland fire, the biomass burning, from the burning the vegetation, you know, for particulate matter, sulfur dioxide, even toluene, it's much higher than the burning of that wildland urban interface, burning of that town. But if you start looking at other compounds on the right there, benzene and HCl, actually burning those structures, burning those cars led to even higher emissions than what we would see from just burning biomass and vegetation. So when we're thinking about public health and downwind impacts, it's really important that we consider what's being emitted from these structures and where they're going and who they're being exposed to. I was personally impacted by an urban fire a little more than a year ago, December 30th, 2021. The Marshall Fire went through my town of Superior and the town of Louisville, just south of Boulder, northwest of Denver. It was a 24-hour fire, and I don't know if you guys can see mine, but actually my house is located right on the edge of the eastern edge of this fire. It was pretty impressive, and I really want to highlight this link at the bottom. Noah put together an amazing story map about the fire, the response, the weather predictions, what happened during the fire, the suppression. It was extremely impactful to me. It burned down the top left plume up top. My house is right underneath the plume to the right. And it just burned houses to the ground. It melted cars. It was devastating to my area. But one of the things that happened after the fire was that I started getting phone calls from my neighbors. And they're like, those of us who still had standing homes in the neighborhoods that were impacted by this fire plume. And I'll tell you what, the whole area smelled. We had smoke in our homes. We had like the black char in our homes. The houses smelled. And everyone wanted to know, is it safe to move in? Can we go back? What do we need to do clean up? How do we know if it's clean enough? So one of the amazing things about this fire is it happened where it did, and the community in Boulder and beyond is amazing and full of incredible scientists that proved to be a huge resources to our communities. And I contacted my friends and colleagues and I said, I'm getting all these questions. What do we know? And we ended up putting together a website to put together all the information we could gather about impacts, air filters, remediation or mitigation after the fire, remediation after the fire, et cetera, and use that as a community resource. And we had this amazing team, Nina Vance and Mike Hannigan from mechanical engineering, Yost DeGal from chemistry, Colleen Reed from geography, and then Abby Koss from TOFWorks. We were able to rapidly deploy measurements. Here, I'm going to skip this one. Instruments across the area in people's homes, and measure what was going on in the homes. Also measure when cleanup people came to clean the house. Did it make it better? Did it make it worse? What happened? I think we provided some of the first measurements to really like immediately after to help people learn what was in their homes, how different cleanup activities worked, how did different fans and filters worked, etc. And these are some of the research questions that we addressed. We are just now getting some papers out, so hopefully by the time I get some next talk, we'll have some great resources to provide people. But I think there's huge opportunity here to better understand not only what the plume produces during a fire and who's impacted downwind during the fire, but also post-fire, and how people are impacted and what happens when it's safe. Right now the remediation companies come in, they do a lot of work. It's not clear to me if all of that is needed, if all of that is effective. And there are still people living in our community that aren't moved back into their homes. And so I think there's a need to do more here. And again, these are some of the things that we're looking at. We did have a rapid funding from my series from our research institute, as well as NSF rapid funding. And I'm going to leave it at that. I really want to thank everyone for joining in. And I'm happy to take questions or follow up. And actually, before I end, John, I just want to plug the Earth Science Women's Network, the ESWN. This is a resource that is available to women in science, or actually to everyone. We run a jobs list. We have professional development activities, and I invite everyone to check it out. So I'll leave it there. And I see Shobha has her hand up. Hi, Shobha.
Hi, Christian. Thanks. Wonderful presentation. Quick question on the algorithm itself for the fire emissions. You mentioned about the field loads, and then, of course, the uncertainty, not knowing exactly the field loads, because, of course, like you take some source values and attribute based on the vegetation map. Is there a reason why your group has not shifted over to doing emissions with fire radiative power, like most other science teams have?
Yeah, just because, again, other groups are doing that. And so this is different and provides a different perspective towards that. It's how the model has been set up. And my understanding is you still need to know something about the type of fuel that's being burned to get the emission factors right.
Yes.
And so there's still that uncertainty there about whether you're burning a forest, an evergreen forest, or a grassland. So that uncertainty feeds into both the FRP driven models versus this model.
Thank you.
Yeah. Santiago.
Hey there. Really nice. Really enjoyed the talk. Many questions. I have two questions. I guess I'll say them both together and you just choose how to answer.
Which one's easier?
Yeah, I mean, can you comment on the status of trying to model the probability of getting pyrocumulus clouds and their potential to reach the stratosphere? I mean, are there any efforts towards that? And the second question, kind of related, particularly in the US, in the West and South America too, you're starting to have more aridification, desertification. So when you have fires now, also you're lifting dust. So to what degree these new sources, like you mentioned, are being started to be integrated in fire inventories?
Yeah, those are great questions. The first, I really can't comment on. I provide the emissions and then let the meteorologists look at the PyroQ, but Dave Patterson and Ed Heyer have done a lot of work looking at that, and I would leave it to them. I don't know how to answer that question very well. I have worked with Maria Valmartin, where we've used satellite data to try to figure out where the plume is going for different types of fires, but it doesn't tell you anything about cloud formation and PyroQ formation. The dust question is really interesting and something that I have not been able to consider as of yet, but I think it is really important, particularly for those big particles, the dust particles, and there's a lot of inorganics and metals in those particles. I think it's somewhere where we need to go, particularly as, like you said, things get dried out. There's a lot of things thrown up there and up high so they can be transported far. If you want to work on it, that'd be great. So, but excellent, excellent. I don't know who's doing that, if anyone is. I think that's a real opportunity.
Well, I believe I've been in conversations with some people and with the Dust Square network, and they have
cool.
yeah, and they've been talking about that too, and not necessarily that something is happening, but it's from the dust people, they're realizing, well, you know, fires are becoming another source for us. So I don't know. I mean, you know, you guys are, you know, you're in the West, so you should talk.
Oh, I think that's excellent. Maybe I'll follow up with you. That's great.
Okay.
Thank you. Should I check the chat, John, or are you?
Yes, we do have a couple of questions from the chat, and I will encourage them to speak out. So, for example, Russell Dixon, Professor, do you want to unmute yourself and ask a question?
So
Sure. Hi, that was fun. How you doing?
good. How are you?
Good, good. I like your background.
Thank you.
So I'll try to keep them short. There's a hard question that will have a quick answer. As has been in the news a lot lately, there were some big vinyl chloride fires.
Yeah.
So they generate HCl and the delightful compound phosgene.
Mm-hmm.
Do you know of any simple dirt? No, okay.
No, but I'll find out. Again, like I work with amazing chemists, I'll go ask them and let you know. I don't think so. I don't know.
So,
off the top of my head.
Yeah, there are lots of ways to measure it, but I'm just trying to think of something quick and.
And you know, we need quick and dirty for so many different compounds. I mean, we had $1 million TOFWorks, you know, PTR TOF that we rode around to get all the chemicals, but like to do something fast and easy in many, many homes, you know, the total VOC sensors, you know, they're as good as they're going to get, right? And they can only tell you so much.
Yeah, they're wonderful, but that's not a quick turnaround and you know, not cheap. And I'm not even sure you'd have to tune it for phosgene somehow.
Exactly.
Yeah, good. So, well, the other question is, I've always been fascinated by the wavelength dependence of the aerosol that you generate when you burn wildfires.
Yeah.
And so does that wavelength dependence of absorption go into your model when you're trying to do photochemical repercussions? No,
I mean, what we do is we provide organic carbon and black carbon. They have defined, you know, this is a huge area of opportunity. There's been so much work from the measurement. Oh no. Sorry, I just got a thing that said my Zoom quit.
No, it's fine.
Yeah. So, but yeah, I think, you know, there's huge opportunity, one from the emission standpoint, you know, to get emission factors that also include these characteristics, because right now they don't. And but there's been amazing measurements that do characterize, you know, this optical properties of these different particles. And then you need a model that'll be able to take that into account. And, you know, I'm using, like, you know, I work with people who use Mozart and ChemChem, and I don't know how well they do that. I mean, it's all parameterized.
Well, yeah, if you're going to have a model that kind of global scale, then you getting down into those details could be tough. But okay, I guess that's good.
Yeah, not very satisfactory, but lots of opportunities for future research. How about that?
That's I was just saying that's a great PhD project.
Oh, yeah. Okay. Yeah. So
we'll get somebody to work with NCAR.
I'm happy. Yeah. And I'm happy to work with any students that are interested in improving this. Yeah, I have one student right now that's improving peat burning in Indonesia, and I hope to expand that to boreal forest. So there's lots of opportunity, and myself and my colleagues at NCAR are more than happy to work with people.
Good. Yeah, yes, pay attention, students. One of NCAR's charges is specifically to to help the universities and reach out to students for collaborative projects, and they do it very well.
That's right. Thank you. That's a nice plug for NCAR. Thanks. So, anyone else?
Hey, Christian, this is Shobha again. I'm curious about your waste burning. So what's the, I guess you have emissions factors.
Yeah.
But like, where do you get the inventory for, like, how much waste is being burned and so forth?
That's a great question, Shobha. We went through so much literature looking at waste production per person, per capita, for different countries. There are some publications that looked at the makeup of trash in different cities. Poor grad students had to do that work. I think that would be a bad PhD project. And then it's just huge assumptions, based, and then we looked into, what percentage of those countries or cities or towns have waste management, waste collection. Yeah, it's very, very uncertain. And I think, again, like there's, we put some large uncertainty bounds on it, but it's happening everywhere. I mean, my first day in Ghana, my first trip, I went and took a run first thing in the morning, and that was a big, big mistake. And it wasn't the biomass burning going on. It was everyone burning their trash when the boundary layer was this low, and the pollution was just awful. And it's some nasty stuff. So, I mean, the amount of plastics in our trash now is so much more so than it was maybe 25, 30 years ago.
Right. Thank you.
Okay, there's one. Are you working with I don't know what PEHSU is. Maybe Gretchen, what is?
Yeah, that's PESU, Pediatric Environmental Health Specialty Units. There are 10 of them across the regions. Regionally here in Region 10, Dr. Catherine Carr has released several studies that have gone international on smoke pollution and to the health of children, both in utero and after birth. So I was just wondering, you've done an outstanding job here. Thank you so much for providing all this information. But I'm very interested in maybe more that comes out on all this wildfire smoke pollution, air quality related issues on children's health that have to live through this, and the cleanup, all the toxic chemicals and others that are in the cleanup post-fire, which creates additional pollution. So I just seed planting, I guess. And maybe that's a PhD study too.
Oh, that's like 10 PhD studies or like 100, right? But
yeah.
I know, and her name is escaping me, and maybe that's who you mentioned, the woman in San Francisco. There's a scientist that has produced a lot on health and children's health. From the exposure to wildfire. Like after the Marshall Fire, we partnered, well, I say we, not me, to do health follow-ups, but I don't know what focuses on the children versus adults or general population. But I think there's a lot of opportunity. I mean, I think there's so much just in general, like understanding the general health impacts of wildfires and urban fires on just public health in general. And then getting at the specifics. So again, there's huge opportunities there. So yeah. Oh, maybe
thank you,
Stephanie Holmes. But yeah, in fact, I just at the AMS conference in Denver this year, Sonoma Tech and Michigan Tech, Nancy French in Michigan, and then another woman in San Francisco, we're all doing work looking at the health impacts and trade-offs to having a wildfire burn versus to do prescribed burning. And so there's a lot of work coming out on that, as well as the trade-offs that you might see in health outcomes if you have these different fire regimes, because we have to learn to manage our forests. And our fires in the West are only getting more intense. The seasons are getting longer, and the smoke is having more and more impact. So, anyone else? Can I stop sharing my screen? So,
Okay.
yeah.
Yeah. Any other questions? Okay. Yeah. Feel free to bring up any last minute questions. And feel free to interrupt me. Okay. So with that, I think we'll thanks the speaker for the great talk, and we look forward to seeing you next week. So next month we'll have a in-person seminar coming up, and we'll provide night refreshment. So I look forward to seeing you there. And thanks, Christine.
Thank
Yeah.
you.
Oh, somebody asked about cumulus and fires, and doesn't Mary Barth work with that stuff?
She does. I haven't seen work with her doing PyroQ lately, but Mary Barth, and then again, like Dave Peterson and Ed Hire at the Naval Research Labs. I know they've been looking into it, but it's something I don't pay as much attention to. Sorry.
Yeah, well, that's just if somebody wants to contact at NCAR, that's who I would.
Yes.
Yeah, and locally it would be Mike Fromm.
Oh yeah, Mike Fromm. Definitely.
He worked with Zhenqing Li here. So he's also with the Navy and NRO.
Awesome. Yeah, you guys are an amazing community there. So
yeah, just like Boulder. So
it
with
is.
anything like luck, we might be out there with a Cessna this spring. We'll see.
Oh, that'll be fun.
Yeah, we'll swing by. Okay, let's see if my students are paying attention.
Yeah, who hopped off? Hi, Chitson. I don't know if you can hear me.
Okay, nice work. Thank you.
Yeah, nice to see you, Russ. Have a good day.
You too. Bye-bye. Enjoy the weather out there.
Thank you.
Okay, thank you, Christine, and thanks, everyone. We look forward to seeing you next week. Bye-bye.
Bye. Thank you, John.